All right, let's go back to part 3. We're going to just do lots and lots and lots of examples. So we previously did L2 norm. Now we're going to do the we did the L1 norm. Now we're going to do the L2 norm. The way you write the L2 norm is with a 2 here. The L2 norm is also called a Euclidean norm. And when you have a vector x1, x2, the way you find the norm is you take the square root of x1 squared plus x2 squared. Now, if you have 3 numbers, like 1, 2, 4, let's do 4. Let's say we have 4 numbers, 0. So if you want to find the L2 norm of this, it's simply square root of 1 squared plus 2 squared plus 4 squared plus 0 squared. So this is what the L2 norm is. Now, I'm going to include the video, a separate video in the link below about norms. You wanna take a look how norms work, so that these concepts are not so foreign to you. Like that video gives you really good like origin story of how norms work. In any case, if you have a function and the function takes the L2 norm of a vector like this, how do you take the derivative of this function? Well, this right here, for example, is simply to the power of 1/2. When you take the derivative, you put a 1/2 at the front, x1 squared plus x2 squared, and then you subtract by 1, so it's minus 1/2. After this, you take the derivative of what's inside with respect to x1. So if you do that with respect to x1, we will get 2x1. And then you take derivative with respect to x2, 2x2. And there you have it. The 2 here and the 1/2 here cancels out, resulting in just x1, x2, 1 over square root of x1 squared plus x2 squared. This right here is 1 over square root. Now, you may notice you may remember from the last previous videos, the very last part is to look at it and see if we can simplify this into something simpler, like in the matrix vector format. So this right here is simply just x, right? We defined it here. And this right here is simply the L2 norm. Therefore, it's just 1 over the L2 norm. That is the derivative. And that's it. That is it. Okay? So that's a derivative with L2 norm, and it's used a lot for this thing called regularization. Both L1 norm and the L2 norm are used quite a bit. So make sure you go and watch the video on the link below. It's really short, like 15 minutes, but it will give you a different perspective of what norm is after you've seen the video. All right, the one after is the PCA objective. The PCA objective, let's say we have X and A, right? So the PCA objective is basically X transpose AX and then X transpose identity matrix X. For those of you that doesn't know what an identity matrix is, it's basically a square matrix where the diagonals are ones and the off diagonal are zeros. So that's a special matrix. We call this I for identity. Okay. Now, this is a matrix. So instead of A over here, we have an I, and we just multiply them together. Lambda is treated as a constant. So this right here, we're going to call it the PCA objective. Later on, we're going to revisit these. But right now, you just need to know how to take the derivative. So this is a combination of everything we know already, right? We can rewrite this as X transpose AX minus lambda X transpose IX plus lambda. So when we want to take derivative of this is a quadratic. This is also a quadratic, and that's a constant, so we can cancel that out. So what's the solution for quadratic derivative? this right here is A transpose plus A times X. And this right here would be I transpose plus I times X and lambda. And since there's a minus here, we'll put a minus here. So this right here is the derivative. Right? So taking the derivative is not hard. What is interesting about the PCA objective is that when you take the derivative, very often we want to find the point where the derivative is equal to 0. But you can't always do it because sometimes the equation is too complicated. However, for this particular case, you can, because you can just find x this way as A transpose A is, let me see, this is equal to 2 lambda I x. Okay? And I can, you don't really need the I. A transpose A. So if we set it to 0, you should end up getting something like this. Oh, I guess I didn't mention how I got rid of that. How I got rid of this. Because this will end up with 2I times x. And yet I got rid of I. The reason why we can get rid of I is identity is special because any vector multiplied by the identity matrix give you itself. So let's say we have a vector 1, 2, right? And what's the identity? Diagonal. Ones is diagonal and zeros. So let's multiply this out. You're going to get this number back, right? You end up getting 1, 2. So identity is property. This is a key property of identity. Any vector multiplied by identity is just itself. Therefore, if x times I is just equal to x, then we can just put x here. So that's how I got this. Okay, next, well, what does this mean? Next, oh yes, I can just put this 2, yeah, I'm going to move the 2 over here, 1/2. And I'm going to call this whole thing Q. So Qx is equal to lambda x. Now, for those of you that have taken linear algebra, for those of you that have taken linear algebra, will recognize this as the eigen decomposition. And this turns out to be the solution for a lot of problems. So knowing how to take derivative of this will help you later on doing this. So for now, you just need to know how to take derivative. Okay. Okay, next one. The Gaussian maximum likelihood objective. So this one looks really complicated. There are like a lot of things involved. So let's break them down. The first thing you need to know is that the log has a very, very interesting property. When you have log of xy, this is equal to log of x plus log of y. So over here, we have a log of the product. So this is what it means. If we have a log of, let's say 1, 2, 3, right? xi. This is equal to log of x1 times x2 times x3, which means that using this property over here, it means that we have log of x1 plus log of x2 plus log of x3. Another way to write this is the summation of the log of xi. So this means that you can essentially move the log inside, which I did, and then convert the product into summation. So because of this property, we can do something like this. And this makes a lot of things easier. And I'll explain to you why. Okay. So based on what we just talked about, I can move this outside and turn it into a sum. And I can move this inside. So the log is inside and the summation is outside. Okay. Now, based on this property again, I can split this and I can split this. Okay. So what after I split this, it's log of this plus the log of this. Now, this right here, when we take derivative later, it doesn't really matter. It's just going to be 0. But um, when you have, so this right here is just a number because it's not a variable. If you add the number by itself n times because of the sum, right? If you have sum equals 5, 1 equals to 3, then you would be 5 plus 5 plus 3, plus 5, 3 times. So this is how I got the n, because you added up n times. So n times this thing. Okay, and this part here is the interesting part. When you have a natural, well, I wrote log here, but we're going to treat this as a natural log. The natural log of a value, let's say x, is equal to y. Okay, and I I don't know if we went over this, but the very interesting property about log is that this right here is equal to e to the y is equal to x. So that's what this means. You have some kind of exponential value to the power of y will give you x. This means that if this right here is e to the some value, I don't know, q, and it's equal to some question mark. Therefore, it's saying that e to the question mark is equal to e to the q. Therefore, the question mark must equal to q. See, we just use this logic, and essentially we're able to identify what the question mark is, which is just q. So what this is saying is that log of e to the anything will just give you the power. So this is very, very useful. We use this all the time. So because of this, log to this, e disappears, and we only keep this portion. We get rid of the log. Well, which results in this. And now we can take the derivative with respect to u, right? So this is with respect to mu. So this, there's nothing here, so we're just going to cross that out. That's equal to 0. This right here is also very easy to take derivative of. Let's see. Let's do over here. So summation I to n 2 sigma square xi minus mu square. So if you take derivative with respect to mu, 2 comes down. So summation I to n 2 xi minus mu 2 sigma square, right? And then you multiply a derivative of mu, which is minus 1. Therefore, it would be minus. So minus, minus cancels each other out. And 2 cancels each other out. So we only have I and xi minus mu divided by sigma square. And that's how we got this one. So taking the derivative of these is it's not easy. And this is also special because later on you'll see that you can also set a derivative to 0. Right? Functions where you can set a derivative to 0 makes your life a lot easier for a lot of reasons. Okay, so next one we're going to go over is called the uniform distribution. But this time, you're going to try it. All right, you want to find the derivative with respect to A and with respect to B. Okay, pause the video, and we're going to move on. Okay, hopefully you pause the video and try it yourself. The uniform distribution. Okay, well, we're going to use that same property where you can move the product outside and we're going to move the log inside. So log inside, summation outside. And now, if we want to take derivative with respect to A or and B, so you take derivative with respect to A and B. Well, we can actually simplify this. Let's see how we can simplify this. This is equal to yeah. So over here, since A and B doesn't change, you're just adding log 1 over B minus A plus log 1 over B minus A plus the same thing. So you're just adding this n times, right? Therefore, this is just n equals to this. After you add it 10 times, just n log of 1 over B minus A. Now, I know log has a lot of properties. So over time, you would need to remember a lot of them. Another interesting property is that if you have log x to some power 5, you can move this to the front. And yes, I know this seems very random property. So this is actually equal to 5 log of x. Okay? So similarly here, this is equal to len n log b minus a to the minus 1. Therefore, you can move the minus 1 here. So it's minus 1 n log of b minus a. Now we can take derivative of this with respect to a and b. All right, if we take the derivative with respect to a, then it would be minus n 1 over b minus a times minus 1. Okay, so that would be equal to n b minus a, which is the first one. Okay, after that, we need to take the derivative with respect to b. So we have minus n log b minus a, and we want to find it with derivative with respect to b. So it's 1 over n b minus a, and that's it. This is equal to this. Okay, so hopefully you follow. There's several log properties here that would really help you. One of which I told you, log of 5x is equal to x log of 5. Like, you can move this down. Another property is that log of x times y is equal to log of x plus log of y. So this is used a lot. So yes, this is not exactly the easiest one to do. Yeah, you wouldn't need to know a lot of these log properties. Okay, so in real life, you need to take the derivative of a function, right? And in real life, there isn't a magic solution book where you can just look up your solution to see if you got it right or wrong. So the way that you can verify your derivative, whether it's correct or not, is, well, one way to do it is basically use Python to verify it. So on the right, I have written the Python code that automatically give you the derivative function. So over here, let's say I wrote, this is the function we want to find derivative of. And then I found the derivative. And I want to know if this is correct. Right? If I tell you guys this is a derivative and I got it wrong, that would be kind of embarrassing for the professor. So I need to verify it. The way I verify is I write the Python function directly in. So this is the function. Okay? And this is the derivative. This right here is the derivative. So I wrote the derivative in already. Now, if you put this command, grad f, so you put function inside this, this is equivalent to the derivative. Or at least if you calculate the correct one, then they should be the same. So after that, what I do is I randomly generate a bunch of numbers and I print out my solution given this number. Like I print out my gradient at the point of x versus numpy's gradient. If I calculated this correctly, then my gradient and the numpy gradient should give us the identical result. So same result here, same result here. So from this, I can see that what I'm doing is correct. Right? This is indeed the theoretical derivative. So this is how you can tell. This is how you can tell whether what you're doing is correct or not, and verify yourself and not embarrass yourself once you start working. I have written a whole bunch of them. That one was for a one-dimensional equation, but the same idea applies for multi-dimensional. So right here, I calculate the derivative for W transpose AW, right? So this right here is essentially like a quadratic. And over here, it's exponential quadratic. So for both cases, notice my theoretical result is identical to the one that NumPy generated. Over here as well, we know that my theoretical result is the same as the NumPy one. And from this, I can be confident that my equation is identical to the truth. It's actually the correct one. Okay, I think I calculated enough. So this particular one is for ReLU. Okay, so we calculated ReLU previously. Okay, now for the final exercise, we need to consolidate everything we learned today. Okay, for each of these functions, what I want you to do is solve by hand. Find the derivative of each one of them by hand. Once you've found the derivative, then you want to use NumPy to verify whether your derivative is correct or not. Right? This is very important because in real life, like you don't have a way to check whether who's going to tell you whether what you get is right or not, right? So you need to know how to verify it. Check your own work. So this is the final practice question, and that's it. I guess I will see you in the next class.